In this lecture, we're going to go over very briefly the Hartree-Fock approximation. This is one of the more common approaches. It was the first approach to solving the question of how you find the approximate ground state given a set of nuclei in specified positions. I should note that this is a very approximate derivation. I'm not going to go into all of the details. You can find those quite easily, and I'll make sure that there are some references in the notes. So we're going to start by assuming that we have electrons in a set of single particle states, which we'll label as before phi A of x, phi B of x, all the way up to phi n of x. And you should note and remember that x is a composite spin position variable. As before, the ground state can be written capital psi, with a capital T on it, meaning it's a trial. Remember in the last lecture or the last video we discussed the variational principle, and so this is a trial wave function which we're going to vary. So we have capital N electrons, and you can write that as some kind of normalization constant times a sum over perturbations of -1 to the power p. Remember that if the permutations, if the permutation is an even number, then that's 1. If it's an odd number, it's -1. We have the permutation operator, and then we just list all of the possible states like this: phi a of x1, phi b of x2, all the way up to phi little n of x capital N. This can also be written as a determinant, which is known as a Slater determinant. So here we're going to write psi t of x1, x2, etc. up to xn. And that's equal to, I'm going to give the normalization constant explicitly here because it's quite easy to see from the determinant. And then we have phi a of x1, phi b of x1, dot, 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 phi n of x1 going along the rows, and then going down the columns we have phi a of x2, phi b of x2, dot, 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 up to phi n of x2. That comes down to phi a of xn, phi b of xn, dot, 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 phi n of xn. And you might care, if you want to try and work out the form of that for 2 or 3 particles, just as an exercise to understand. Now, the way that we're going to do the Hartree-Fock approximation is we're going to say that the expectation value of the energy is given by, oh, I've gone wrong there, excuse me a second, expectation value ET is given by capital psi t acting on the Hamiltonian capital psi t. And remember that the Hamiltonian is made up of the sum of the kinetic energy, the potential energy, and the potential energy comes from 2 separate terms. One is the interaction between the electrons and the nuclei, and the other is the interaction between the electrons and the electrons. And in order to find the ground state, we are going to vary the single particle orbitals. That's important to understand. So that's the set phi a of x to find the lowest, to find the ground state, which is what given by the lowest value of ET. In order to do that, we need to evaluate the energy. We need to evaluate the terms in the energy. And so we're going to consider that in 3 parts. So the first part is going to be the expectation value of the kinetic energy, which is given by the simple bracket notation, psi t minus a half sum over I is equal to 1 to capital N. And notice that I'm using atomic units here, so the h bar and the squared and the 2 and the m have gone to 1. So we just write it simply like that. Now, we can simplify this enormously because it turns out that we can assume the single particle orbitals to be orthogonal or orthonormal. So we assume that phi a is orthonormal, and that means that given all of the terms in the trial many-body wave function, there's only ever one term on the left that gives a non-zero result with the term on the right. And you can see that that's reasonable because we've only got a single position in the operator in the middle of our expectation value. Now, if you follow the maths through, you can show that that gives you a sum over the individual single particle kinetic energies. So we're going to write this as the sum over I is equal to 1 to n of phi I minus a half del squared phi I. So it's a sum over the single particle kinetic energies. Turns out that the same thing is true for the nuclear electron potential energy. We find the same for the same reason. For the electron-nuclear interaction. So again, we can write expectation value of v hat, which is written as the trial many-body wave function times the sum over I is equal to 1 to n of little v of Ri, where those are the individual positions of the nuclei, the individual positions of the electrons, can be given again as the sum from I equals 1 to n of phi I little v of r phi I. The term that is more complicated, because it has two positions in it, is the electron-electron interaction. So this is where we find the complications and the interesting physics going on. And we'll find that there are actually two terms. So we have one term which is written in the form, well, there's a general set of positions that we can write it in terms of. So it's a simple electrostatic, so it's the interaction between two charge densities. And we write it like this. So you have a half to avoid double counting, s not equal to t, so that's the two orbitals that we're going to be dealing with. We have a double integral over two positions, dx1, dx2, and we're just going to assume that the spin can be dealt with simply for now, of phi s of x1 squared. So notice that that's effectively a charge density. We have 1 over r1 minus r2, and again I'm using atomic units, and we have phi t of x2 squared. And this is often known as the Hartree term. That's relatively simple to evaluate and is a standard part of any electronic structure code. The second term is where the quantum mechanics comes in, and this is an exchange term, and it is also more complex. It's also negative. You can show that just by thinking about permutations. So again, we have minus a half s not equal to t. We have a double integral dx1 dx2, and now what we find is we have phi s star of x1 phi t of x1. Again, we have the electrostatic operator r1 minus 1 over r1 minus r2, and then we have phi s of x2 phi t star of x2. So you might like to compare those two terms, and you can see that in the first term the x1 coordinate was only found with phi s and phi s star, so we could make the square modulus, whereas in the second term that is not the case. And this second term, the exchange term, is it's incredibly important quantum mechanically. It's something that density functional theory does not evaluate explicitly, and we need to be aware of that. We can, if we want to, actually add back in the s equals t terms in both of those sums, because they cancel each other out exactly. And that makes writing the sums just a little bit easier. And so in this case, we find the following. We have a Hartree energy, which is just a half sum over s and t of the double integral dx1 dx2 of phi s of x1 squared phi t of x2 squared divided by r1 minus r2, the modulus, and the exchange term is minus a half the sum over s and t, double integral of dx1 dx2, and then we have phi s star x1, phi t of x1, phi s of x2, phi t star of x2 all over r1 minus r2. Hartree-Fock is not generally accurate enough to be useful these days, but it does form the basis for most of quantum chemistry. A lot of the perturbative methods are based on it, and the exchange part of Hartree-Fock is often introduced into DFT in the so-called hybrid functionals. DFT is much more accurate than Hartree-Fock, and it's also computationally cheaper. It scales with a lower power of the number of atoms in the system, and that's what we're going to be aiming for in the next few lectures. But the Hartree-Fock approximation is relatively simple, it's easy to understand, and it's an important basis for further developments. So I'm going to stop this lecture here, and I would advise you to read the notes and go over any parts of this that you didn't understand properly and bring them to the discussion session.